Hey class, welcome to our lesson on 9.2, solving quadratic equations by graphing. For your warm-up, I want you to graph these three parabolas. Go ahead and go use Desmos, graph them up, and find those things out. Once you have them graphed, make sure you put them into our Canvas page. You can take screenshots or you can type in what you have. Here are three learning targets for the day. We're going to be able to solve quadratic equations by graphing them. You can use the graph to find and approximate zeros, and then solve some real-life problems that go with these. So here are some keynotes that I do want you to write down as you're working through these notes. We're going to highlight a few of them here. So the first things first, a quadratic equation, again, is ax squared plus bx plus c. That's our standard form. We've been hitting quadratics a lot this semester, especially the end of it. You have already practiced solving them by factoring, in which you find the x-intercepts. Now today we're going to work on graphing them. So down here we have our steps, and it shows us step 1, write it in standard form, so get it equal to 0. So if it's not equal to 0, get it equal to 0. Then we're going to take that equation and we're going to type it into Desmos. And then any of our x-intercepts, that's what we're going to find. So our first one here, we have x squared plus 2x equals 3. So the first thing we're going to want to do is rewrite this in the format x squared plus 2x minus 3, because we have to move that minus to the other side. Then once we have that, we can go ahead and graph it into Desmos. So notice how I've already have done that here. So you should have this equation written out underneath this, and then you can have your graph picture here. Now on this graph picture, again, the key points highlight in gray right away. We have our vertex down at the bottom. We have our y-intercept, and while both these things are important, that's not what we're looking for. What we're looking for are x-intercepts. So we're looking for -3 and +1. Now remember, we want to put our intercepts in coordinate form like this when we're doing tests and quizzes. In homework, it might say just x equals -3 or x equals 1. That's fine, but you got to make sure as we're using these as we move forward, we're actually saying the x-intercept using the coordinate form. So that's our first one. Our next one here, again, same type of format. So first thing we want to do is rearrange this into standard form so it's equal to 0. Now if you type this as is, you'll notice how it's not a quadratic anymore, it's a straight line, which is why we're going to need to rewrite this as the +16. If you put equals 0 here, there technically becomes a line. We can talk about that in class in our lessons, but we're not going to talk about that one here. We want to keep it in our quadratic form. We want to keep it in parabolic form. So you'll notice this one only has one real solution because it only crosses our x-intercept once. So bam, we have one solution here. So our solution for this one is 4, 0. So with this problem, again, the first thing you want to write in your notes is what's written here. And then you want to write what we rearranged it to, x squared minus 8x plus 16. And then our x-intercept for this one is at the point 4, 0. This one, the x-intercept is the same as the vertex. Just happens that way. It doesn't really mean anything. Again, we're only caring about when does it cross the x-axis. Our next one, we have this here. So we have to set this equal to 0 first. We can go through it like this. So again, we're going to start with adding that x squared to the other side. So we have x squared plus 2x plus 4. So this one, you'll notice this one does not cross the x-axis at all. This one here is one that, because it's not crossing our x-axis, it does not have any real solutions. So you can take this one, you can rearrange it into this format, but our last part is there are no answers, there are no x-intercepts, so there are no solutions for this one. All right, so big summary here, there will be 2 real solutions. If there are 2 real solutions, then it has 2 x-intercepts. If there's one real solution, then it has 1 x-intercept. If there's no real solutions, then it has no x-intercepts. So we've seen examples of all 3 of these now. The next one here gives us a different type of equation. So it says right away, hey, let's just graph this up. So we're going to graph up x minus 3 binomial times the trinomial x squared minus x minus 2. And you'll notice we have a third power curve going on. this is very similar, and again, just putting this in context, this is very similar to if we had something to the third power here, because it's going to go up and come back down. It's going to do some things here. So as we're looking at this one, if it's saying find the zeros, we simply need to identify the 3 points where the x-intercepts are. Again, zeros and x-intercepts are the exact same thing. So we'll use those terms, we'll interchange them a lot. So make sure that you have them understood that x-intercepts and zeros are the same thing. So if it says find the zeros, it simply means find these 3 points. So for this problem, you could identify all 3 of these points to be the points that would make this whole thing equal to 0. Our last problem here that we have is approximating the zeros of a function. So we have, if the graph of f of x is x squared plus 4x plus 1, figure out to the nearest tenth. So sometimes they'll be really nice graphs, they'll be really smooth. Other times it won't be smooth answers. And what I mean by that is this. Oh, and I made that equals, I should have made that plus. So you'll notice here our x-intercepts have decimal values to them. So in this case, when we say approximate it to the nearest tenth, our 2 answers here would be negative 3.7 and negative 0.3, because this 6/8 would round up that 2 because it's the nearest tenth. So that's something you guys will need to make sure you make note of. All right, here's our last example from lesson 9.2. This one here is a real-world application. So the first thing we want to type in is our equation. So it says, here's our equation. We have negative 16 t. In this case, we're just going to use x because Desmos won't recognize t. So just replace the t's with x's here. Plus 75 plus 2. So you'll notice right away when you look at this graph, there's a lot of things going on here. The first problem it says is find the height of the football each second after it's kicked. So you can do this a couple different ways. You could do the classical way where you type it all in. You could also do it where you say, hey, this is going to be our equation. So we're going to have our seconds of 0, 1, 2, 3, and 4. We see over here at 5 seconds it's negative, at 4.7 it's done. So you could type in each of these numbers into this equation and you get answers that way. So that's one way to make use of that one. Then another way you could say is, you want to actually make this equal to the equation that we have. So we could say negative 16 x squared. Let's get rid of that y1 plus 75x plus 2. Oh no, don't do that. And you can have Desmos graph it for you, so you can get exact values this way. So that's another way you can make use of this. You can just say, hey, I'm going to use these x values to say this is what I want. You got to make sure those x's are the same. Notice here how I have that subset 1. It doesn't work. I had to make sure those things were exactly the same. So that's one way you could make use of this. You'd be able to goat this out, and we get these 5 different dots here of where they are. But the real question that gets asked is estimate when the height is 50. So we know our height is 50. So if height is 50, I could say 50 is that. Now I could really say, hey, I have 2 times height is 50. One of the times I have is at 0.76 seconds, and the other time I have is at 3.926 seconds. So this should make sense because the ball goes up, it hits 50 feet at one point, it goes all the way up to the top, and then it comes back down. It's got to hit 50 at another point as it comes back down too. So this is a different type of question. This is not asking about when it lands. If it's talking about when it lands, we'd have takeoff here at 0. We'd have landing here at 4.71 seconds. So that's something to make note of. These points up here are simply saying when does it hit 50 seconds. So that's it. There is a homework associated with this one. Make sure you guys are working on that homework and getting it done. Have a great day.